Hello, and welcome back to my ongoing coverage of the OceanGate Titan submersible tragedy. This video covers the first half of the testimony given at the US Coast Guard's public hearing by Bart Kemper, Senior Principal Engineer of Kemper Engineering. This testimony includes a lengthy presentation that spans this whole first half and continues into the second, though there will also be some questions from the Coast Guard at the end of the next part too. In this video, the presentation focuses around codes and standards, a lengthy look into the design and analysis of the viewport manufactured by Hydrospace for OceanGate, as well as a brief section regarding Titans, or Cyclops 2 as it was then named, O-rings and end domes. So this testimony does tie in with the previous one of William Conan of Hydrospace, and similar to that one, I know these types of testimonies may not be for everybody, and honestly, I myself got slightly lost or didn't fully understand a couple of moments in this one, though things are made clear, and then after editing the video, I think I have a pretty good grasp of it now, at least in terms of what was trying to be communicated. There is just a lot of information to take in is all, but it is relevant information, as we hear how, as well as slides in the presentation being those that were sent to OceanGate, Mr. Kemper also produced and submitted material for use by the NTSB to aid in their investigation. So again, I know these types of testimonies are not stacked with, say, juicy, behind the scenes type of OceanGate stuff that we've heard in previous testimonies, but regardless, these are still important to fill in remaining gaps in information and to provide more context to the whole picture. Anyway, I will save my remaining words for the end of the video, but I just do want to thank you all very much for watching. It is greatly appreciated. Now, let's begin and hear the testimony given by Bart Kemper.
We will now hear testimony from Mr. Bart Kemper, Senior Principal Engineer with Kemper Engineering Services. Good afternoon, Ms. Kemper. And I want to start by saying thank you from the board for volunteering your firm's services to help us analyze some of the complex data that we had for this case. The expertise you provided was appreciated in this field, and before we started, I want to say thank you for that.
Understood. Thank you.
At this time, you have a presentation to go through, and if you would start with that, and then we will probably ask questions as you go, or before we get to, through the factual side, we'll probably stop and have some questions for you at that time.
Understood.
Thank you, sir.
Okay. Good afternoon, ladies and gentlemen of the board. My name is Bart Kemper. I'm the Principal Engineer with Kemper Engineering Services, and this is the summary of preliminary findings regarding OceanGate and the loss of the Titan submersible. I need to say that this is a unclassified open source presentation. Nothing here represents the opinion of the U.S. Coast Guard or Department of Homeland Security, nor am I expressing the opinions of any other organizations such as American Society of Mechanical Engineers, Marine Technology Society, National Society of Professional Engineers. The only organization I'm representing is Kemper Engineering Services. The intent of this presentation is, as I said, preliminary findings. This is where we are right now based on the information available. It is the intent that if we find things that perhaps are contested or say they are incomplete, that would generate more information. If there's any other information or data available, we'll be happily incorporate that in subsequent work. Our task is to basically provide additional technical expertise in a variety of areas: engineering design, organizational impact, codes and standards, study of verification, validation, and uncertainty quantification. This phrase comes up a lot, VVUQ. It's often spelled out, but just in general, if I say VVUQ, that's what it's about. The acrylic windows is a big part of this, as well as pressure vessels under external pressure. Also, we have expertise regarding carbon fiber composites, computer modeling, and volume failure analysis. Timeline. My first meeting, our company's first meeting with OceanGate was in 2016 at an underwater intervention MTS, Marine Technology Society meeting. Both our company and their company had presented at that time, and we met socially. 2017, Will Conan asked me to look at a non-standard window. I didn't know the company. It's just amongst our own community, we ask each other for help. So he said, give me a look at this, and I did. Made a short summary report that will be talked about later on, but it was transmitted to OceanGate. The key aspect is that it indicated failure was likely after a number of cycles. In other words, it would reliably cycle at least a couple times and not fail, but it did not exhibit the same characteristics that a properly designed window would normally exhibit in terms of stress and strain. The much talked about letter was offered to me by Will Conan, the one that was at the time going to be through the Marine Technology Society. I agreed to sign it. As it's already been discussed, signatures never happened. It was never transmitted. It's outside the scope of MTS, but I was a willing participant of that. Unfortunately, in June 2023, the Titan was lost at sea. Because of my prior knowledge of the windows and my duty to report being a licensed engineer, I put together a report and submitted it to the National Transportation Safety Board regarding the Titan window, just to complete the record and make sure that information was available. And because no good deed goes unpunished, we were asked this March to assist in the Marine Board of Investigation to provide additional expertise. Briefly, I understand my CV is part of the record, but just briefly, I'm the principal engineer at Kemper Engineering Services since it formed in 2006. I'm also an engineering researcher at the University of Louisiana at Lafayette. I'm a retired lieutenant colonel, U.S. Army Corps of Engineers. I did a bunch of schooling, and I did a bunch of Army stuff, and they left at 28 years. I've been doing engineering for over 30 years. Started consulting in '97. So here's where the appropriate work is in '98 I began working on saturation diving systems, which are pressure vessels. That was based on my previous expertise in pressure vessels for the petrochemical and other industries. That continued to happen. I began working with different diving, subsea, and marine companies. I worked with the ACG DSV Eagle, which dove on the Kursk. I worked with different window manufacturers. I also have been worked on and have consulted with Woods Hole Oceanographic, OceanX, and Navy Deep Submergence regarding small subs and various window issues. I've been working with a private individual regarding the Perry PC 1601 lockout submarine. And we've been in negotiation with Reynolds Marion's Hypersub to assist with that when certain milestones are reached with that company. I've been with the ASME. ASME is American Society of Mechanical Engineers, Pressure Vessels for Human Occupancy, which is PVHO, Codes and Standards Committee since 2008. I've been the chair for the Viewport Subcommittee since 2016, and I'm the chair for the Design by Analysis for Glassy Polymers Task Group. That is basically, we're trying to develop a methodology to use modern engineering techniques for any sort of glassy polymer, primarily acrylic, but also polycarbonate and other transparent items. So that has given me a whole lot of work with that area, and that's an all-volunteer group, but that particular task group has people who are not part of the PVHO committee. That's where I work with people from NASA, from Reynolds Polymer. There's a wider, more technical group involved with that one activity. I'm also a member of the Verification, Validation, and Uncertainty Quantification subcommittees on solid mechanics and artificial intelligence and machine learning. Licenses, I'm a professional engineer licensed in multiple states, including Louisiana, Texas, and Washington State. I'm also licensed in Australia. I'm a board-certified forensic engineer, fellow of ASME. Also, I'm a fellow of the National Society of Professional Engineers, editor-in-chief of the Journal of National Academy of Forensic Engineers, and member of a bunch of other stuff. I listed all the ones that apply to this field. I've published 12 peer-reviewed papers and 20 conference papers or presentations that are about either PVHOs, pressure vessels in general, subsea, or VVUQ. So this is the team that we have. I'm the lead investigator. The KE staff are full-time people or full-time associates. Pretty much most of them are all in the Baton Rouge area. The consultants are a bit more widespread. These are all people who are standalone professionals who've agreed to contribute their time. Of note, 4 of the individuals are either current or past members. Well, if they're past members, they're actually still corresponding. They're still part of the discussion, but they're not active voting members of PVHO. So we have significant depth in PVHO. And we also have 3 board-certified forensic engineers. These are people who are used to going through these issues and used to going through documents as well as looking at the engineering side. This is a brief by exception. In other words, we've had gigs of information provided by the U.S. Coast Guard, and we found a lot of good things and a lot of other things. For the purpose of this briefing, due to the time limitations, most of it is going to be focused on the issue involving the implosion. We've also been asked to talk about the role of engineering codes and standards and jurisdictional authorities and innovation as opposed to using, as it applies to using VVUQ. Our initial results are focused on the window design, the pressure hull, the issues regarding testing and simulation, and we've also some of the top levels of operation safety procedures. Our observation is that the larger macro issue is that there was not a integrated life cycle systems approach, and there was not a singular responsible and charged professional as an engineer. So, codes and standards. These are things that we say are written in blood, and this is not hyperbole. The original codes and standards were building codes and boiler codes, and the whole reason they came about was because people were being killed because they weren't built right. So, in both cases, the government basically said, professions, police yourself or we will. So they started making different associations to develop these codes and standards. Boiler started incorporating the pressure vessels. And so this is one of the larger, more in-depth codes and standards, but there are others out there. These codes and standards are intended to be best practices. So it's not always programmatic. Some of them are very cookbook, where step 1, step 2, step 3. And other times where there's more mature applications, then it's more about providing that judgment. These are developed by volunteers. That came up earlier with Will Conan, but everyone there is volunteered. Now, you might be employed by a company such as General Electric or the U.S. Navy, and you're there as an employee and representative of your employer, but ASME doesn't pay for you. No one pays for your way, you pay for yourself. As a small consulting firm, we've paid our own way all the way through. Also, these codes are not just like a industry code where a bunch of people get together in a room and settle it out. These are also reviewed by ANSI. So they look at whether you have a mix of people. For example, in pressure vessels, they look to see you have fabricators, you have end users, you have regulators, such as the National Board Inspectors. In PVHO, we have a Coast Guard representative who is there for saturation diving. So we have these mix of interests so that you just don't have the fabricators or just the owners. We even have divers who are there just as divers. We had the head of ADC, which is the ADCI, which is a professional group for commercial diving. He was there to represent divers in the diving section. So if the owners were trying to push too hard in one direction, we want this because it saves money, he would be pushing back saying, yes, but this is safety. And be able to explain it to the other members, such as me as a consultant, and we would ask questions of each other. So it's very much a dynamic, and it takes a while to make things happen. But it's that mix of interests and that longevity in activity that we can draw upon that makes it happen, which is also why when you talk to people in these Codes and Standards Committee, as you've been hearing, I know so-and-so, I know so-and-so, this is why this happens, is that in our volunteer time, we've made these associations and we help each other out. New technology does happen, and that's what has come up often, is like new technology doesn't it stagnates. It takes data. You're trying to convince people to change a safety standard. And once it's published, anyone can use this standard. So it's not a question of, I trust this company, or I do this a certain way, I'm the best thing ever. That's not the point. When you write these codes and standards, anyone can apply them. And they have to be written in the sense that the only thing the person will see are the words on the paper. So it's very much like military writing policy. You have to be specific. You have to understand. You'll have E4 mafia lawyers out there looking to sharpshoot you. You know, you have sergeant majors out there trying to figure out how to implement it. It's that kind of thing. Interesting thing about the American system. The different alphabet groups, ASME, ASCE, all these different engineering groups that write the codes and standards, cannot enforce them. There was a Supreme Court ruling that made this absolutely codified. But the reason being is if we were writing these books over here, and then we could enforce them, then we'd be part of the government. So we can't do that. So what happens is all these codes and standards are best practices, and they're just put out there, and it's up to the jurisdiction to decide to adopt them. So this is why there's different building codes throughout the United States. We have converged mostly on the International Building Code, but there's still other building codes out there. For example, with the PVHO code and the Coast Guard, you guys added in the CFRs, when you say we are adopting ASB PVHO1, you added, we will also want an additional 16th inch corrosion allowance. That's not in our book, but it's in the code. And as the jurisdiction, when you enforce it, you're looking for that corrosion allowance to be specified in the drawings. The jurisdictions can add, subtract to the code, as well as decide how to enforce them. So this actually does a lot of good for writing the codes, because we can focus on the engineering and on the safety aspects, and let the jurisdictional aspects and the politics and all that be literally someone else's problem, that we're not allowed to get involved. It is a system of codes, and by that I mean with PVHO, we refer back to the National Fire Protection Association for all the fire requirements for medical hyperbarics oxygen, because they already wrote those rules. We don't need to redo those. ASCE 7 is American Society of Civil Engineers Code 7. That's the code that so many codes, that all these other alphabets use for wind loads, snow loads, seismic loads. So these codes generally defer to the other expertise. Even within ASME, there are separate code committees for piping that is and bolting and bolted joints, which is not the same as the bolts themselves. They all have their own committees, and they all working independently, but they are brought together, homogenized. So when someone says we're not going to use a code, they're rejecting this large body of knowledge. It's not just the people in one code group that's contributing to this. It's an interlocking system, and generally speaking, these codes and standards are built on decades and decades of experience. The reason why we've increased design safety margins in the pressure vessel code is pretty obvious. You want things to be safer, but it's counterintuitive. In 2000, we reduced them. We actually reduced the design margin. The reason being is that the original design margins were based on old technology and a lot of riveting and a lot of things in the 50s and 60s. We didn't have non-destructive testing. We didn't have the ultrasound. We didn't have the radio that we have now. And the mills were more precise. The mills were much more reliable. So based on that and a lot of studies, we were able to back off that design margin a little bit. So that's an excellent example of how changes in technology is not just about make it harder, make it harder. If you can prove it safe, we'll make it easier. Slide.
Mr. Kemper,
Yes.
This is an important point I want to focus on
Yes, sir.
briefly. Can you provide an advantage that would be realized if the government incorporated ASME standard, for instance, into the regulations versus just updating the regulations?
Oh my God. So having been on both sides, having been in the military and worked in with civilian agencies versus what we do here, it is very challenging for the government to keep up with codes and standards, because that's a secondary thing, because that's really not a central role. Further, when it comes to anything involving the military often has a 2 to 5 year rotation, so you lose expertise on a regular basis. And you're not going to be able to pull together that expertise the way the different alphabets will do. Where it makes sense to do that, if it's military specific, service specific, such as, let's say, issues involving the F-35. Then you would have the end users, which is the Air Force, and then the various contractors that work on that system develop it. And that would be the manuals and operating procedures. That's where that makes sense, because it's all in that one tight community. But if you're asking the government to look out upon the vast area of any one industry and be knowledgeable of that, that's not realistic. You're going to need the help of that. And so kind of splitting the difference is what is happening in many of these areas, such as PVHO, where there is a U.S. Navy intense interest in that code, as well as a Coast Guard intense interest in that code. They send reps. There's a seat available for the FDA on the medical devices for PVHO. So the government can have a say in it and be a voting member and be informed. But if the government was trying to keep up with it, they just generally, it's a challenge. A good example is there is a MIL standard for active and passive barriers. And that was developed originally in the 60s and 70s. It was updated many, many times during the War on Terror. And they're now trying to bring that over to the ASTM codes and standards for Homeland Security. That's another one I'm on. So that's why I'm aware of this one. So this is something that was normal, that used to be more or less run by the Corps of Engineers and the Air Force labs, and is now being transferred over. They still have representatives from those groups as part of the codes and standards group, but now it's going to be run by ASTM and be able to be regularly updated and not be subject to government shutdowns and not be subject to changes in policy, because it's not just about the government, it's going to be about the industry as a whole.
Thank you, sir.
Okay. So just to give a very brief overview of the pressure vessel code, it's big. 13 sections, 34 binders, it ain't cheap. But it covers so many rules and so many methods for these different pressurized applications. It gives you all the material data. I mean, we're dealing with material data right now with this project. Well, everything that is done with this code, there's 4 large binders that has all the material data, the specifications. It gives you the yield strength and allowable stress and tensile stress versus temperature for all these different alloys and their different grades. It gives you their welding compatibilities. It gives you all this. This has all been worked out. So as a design engineer, I go, well, I want to do this, and it's one closed system. The testing is all done. And that's the thing, is that if you want to bring a new material into this code, you have to submit all the testing. There's a whole protocol for that to get your new alloy into this book. So it can be done, but you have to prove your stuff, and then you have to provide the data, and it's vetted. Related to this, there is a joint code, API's American Petroleum Institute 579/ASME Fit for Service 1, where this is looking at calculating the reliable useful life of items that are in service. So if something was in a fire or dented or corroded past the original corrosion allowance, you could make an informed decision what would be a safe, reliable, useful life of this. Maybe downsize the pressure, maybe make it a repair. It also would give you justification for making a repair versus scrapping. So, and then we'll talk more about PVHO, but it was originally focused on Windows, and now the important part is it now looks at PVHOs as a system. So we look at now not just as a pressure boundary, but we're looking at as how we're going to keep the people safe inside. But all the number crunching of how to make the pressure boundary itself, with the exception of the window, either reverts to ASME Section 8, or in the case of submarines, goes to the classing societies. So that's an example of how you stay in your area of expertise and your focus, and you defer to other codes and standards. So again, this is the system that was pushed aside, and why we have to look at this. So this is the standard, and if you're going to do something different or use something different, let's say a foreign code, the question is, does it achieve the same level of reliability and depth of understanding that this code does? If you normally are specifying ASME pressure vessel code, which is used internationally, it's not just in America. then this is a level of reliability because they've reduced the uncertainty by looking at all these different areas in detail, testing the materials, working out the different calculations, working out what are the allowable tolerances when you're putting these inputs in. All that's been worked out. So PVHO. So specific to the situation here, there is different sections. There's section 7 is submarines. And in it, we have a requirement for a user's design specification for every PVHO. This is not required in all pressure vessels. It is required for some of the Section 8 Division 2. Just go with me on that. You don't want me to go into all the arcana there. But we require it for all PVHOs because it's important that we're not just making steam here or holding acid or whatever or making a chemical. We have people inside. And most pressure vessel codes don't even start until you have 1 atmosphere of gauge pressure. You're holding one pressure, 14.7 psi or 15 kPa. Here's 15 kPa, which is 2 psi. The reason being that 2 psi is a threshold where you could have an injury. That if you're at 2 psi and the door pops open or the window pops off, you could have an injury. Now, not always. You can have but that's the threshold that has been medically determined back in the 50s and 60s, and we're still seeing papers come up through different medical groups that they're still seeing that is, people getting injured at even 1.5 psi rapid decompressions or impulses. So we've been using 2 psi as a threshold. So that's one of the things that happens is that you normally would not worry about doing a half atmosphere pressure vessel for normal uses, but if you're using it for people or animals, you invoke these rules. Now back to the user's design specification. I've cut and pasted most of the one for submarines. What's important here is the section, and pardon me, but I am at an age, is it specifies that you must say number of intended occupants, maximum pressure depth, maximum pressure and depressurization rates and event rates, and conditions where these rates may be maintained, the intended operational environment. Think about this. The metallic hull of a submarine is going to be good pretty much in the Bahamas versus the Arctic. But the windows are plastic, and they have wildly different strengths and stiffnesses as you go across even a 10 degree Fahrenheit excursion is going to be as different as a 50 or 100 degree excursion with a metal. So if you're going 50 degrees with a plastic, it has a pretty significant impact on your design. So if you don't say up front, we're going to be going at this temperature, it might be missed. Maximum number of pressure cycles, maximum minimum internal external pressures, operating temperatures, and storage conditions also have to be specified. That's right there in the code. Because how you do all that defines the life of this item. So without this information, an engineer cannot do their job. So these are, to most people, these are like all common sense. Why wouldn't you do this? But we put this in the code because these are the critical things you want to put in the checkpoint just to guide people to make the right. You don't want to have someone skip something like, oh, I didn't think about where I put it up in storage, and you're already halfway through the design, or you already built it. And you assume that, oh, I would just assume that you'd put it in a garage and keep it safe. It's like, no, we're putting it out in the back pasture. You didn't say that. So that's the kind of thing that needs to be specified. Now, there are other reports. There's a GR1, which is a manufacturer's design report. That is a form that a professional engineer signs off on that says all that stuff in the user's design spec, which doesn't have to be an engineering talk. It can just be explaining, I want this many people, I wanted to do these things. The manufacturer's data report says what we designed meets all this. It performs. Here's how it performs. And that you have the mathematical models, the calculations, and the drawings to back it up. And there's a number of drawings and a number of documents that are also required by code. So when there is an issue with a pressure vessel, particularly a PVHO, there's automatically paperwork that goes with it that guides people to examine any sort of post-incident question, or you're just buying and selling it. You get its pedigree. This way you don't have to say, oh, trust me, it's metal. I have seen pressure vessels being sold. Well, it's steel. Which kind of steel? Steel is steel. At that point, all the engineers' heads explode and get really angry because it varies wildly. So this is why, even aside all these other rules about how thick it is and everything else that has been talked about in the past, from a engineering reliability point of view, an engineer design point of view, that's why these documents are important, because it's not just about how thick the window is, it's guiding you to how you approach your design and document your design. So how this came about was Jerry Statue was faced a problem. During the Trieste dives, they first used glass, because glass makes sense, and then they had problems with it. So they said, I got a better idea. We're going to use sapphire, synthetic sapphire. The problem with that is that as it sits on a 45-degree angle, 90-degree frustrum, or 45-degree angle, the problem is that you have this very, very, very stiff ceramic and steel. At some point, as you go down thousands and thousands of PSI building up, water will find a way to jet through. And around 10,000 PSI, a jet is the same jet they use for cutting steel. So if you ever had to do a steam trace where you have to wave the broomstick in front of you walking down a steam trap, and when the stick gets short, you stop, it's the same issue, only worse in a lot of ways. Dr. Statue figured out that acrylics, and believe me, it was from talking to people from that time and reading about it at the time, it does not sound like a good idea. Acrylic is used for toys. Using this for going deep in the submarine makes as much sense as using carbon fiber. Why would you do this? But he figured out if you make it the right way, what happens is when you're on these conical frustrums, which is the fancy name of saying the cone on the seat, that little bit of plastic squish keeps it sealed. And more importantly, the failure mode for these hard ceramics is often a crack that propagates in an unstable manner, that by the time you see a crack, it may be already fractured. Once it fractures, it loses the strength, and next thing you know, the inside becomes the outside, and when you're in a submarine, you really don't want to have a convertible. Whereas with acrylics, it is more likely to form a stable crack. First little cracks can be called crazing, and that is your warning to stop and reduce pressure. And of course, if you're in a submarine, reducing pressure means go up. But in a medical device, it would be back off your pressure. So do what it takes to stop yourself and then depressurize. And the US Navy agreed that was a good idea, and they spent about a solid decade testing different shapes, different ideas. And the thing is, being plastic, it's not going to be elastic. And this is where we're going to get a little bit of engineering. I'll try to keep it very simple. Most things we do, like your car, your use of steel, is elastic. If you put a load on it, it might move a little bit, but it pops right back. It doesn't do you much good to have things that bend and break. But if you take a piece of steel and you push enough force on it, at some point it bends and stays bent. That means it's gone plastic. And right there in that corner where it bent up, that's plastic bending. This is plastic all day long. There's a short little regime where it's pure elastic, but then it gets a little bit more plastic and a little bit more plastic. It's called a plastic for a reason. It's plastic. So he had to come up with a way to make this work. And there was a lot of physical testing. But the computational tools were not there. To do an elastic design, usually it's very simple calculations. The only material characteristic you need is what's called the modulus elasticity, E. Whereas when you're doing nonlinear work, you have a whole stress-strain curve you have to incorporate, and then possibly have a creep curve, and then you have temperature effects. Modern computers can do this now. But back then, what he said is, we're going to test the heck out of it, test it repeatedly, get statistically significant data sets, figure out what the curve looks like. And you see a curve right here, where you see a bunch of, on the left-hand side, you see a bunch of little dots for different data points that shows, okay, that's where the brakes are. And then when he developed his design curve, he just stayed the heck away from that. So when it comes up that it was a very, very conservative curve, yes, it was. He understood there was a lot of uncertainty. He understood that we could not, at that time, reliably compute a model to predict it the way we could with steel. So facing that uncertainty, he tested the failure a bunch, figured out a failure band, wasn't a solid line, a band of failures, and then put the design line well away from that. So that was the process used. And the significance of this is that to date, as of today, we have yet to have a window designed, a PVH-01, that was manufactured to standard and put in properly and not see an abuse. In other words, you weren't a submarine that took your window down to a thermal vent. You didn't decide to put a heat lamp on next to a window to warm someone up. You did, as long as you don't do those things, there's been no design failures. They've had things that they take out of service at the end of design life. Again, that design life is conservative, but there's been no failures. So when anyone says it's a very conservative standard, they're absolutely correct, because Dr. Jerry Statue was terrified of anyone dying because where he put the curve. So he put that curve where he felt it was safe, and it's been proved out. The problem with this is because it's all empirical data, you can only use the shapes in the book for the material in the book, and that's it, because it was all done empirically. Further, you're not even putting the material specs into your calculations. We'll do the exercise in a little bit, but if you double the strength of your material, you can make it thinner or lighter or something. The way the system works is, as long as the material specs meets the minimums, you go through the book and you use the magic charts. That's it. So there's no way to really innovate at this point, which is why I've been working on the Design by Analysis group. So we are looking at doing that. We are responding to the needs of industry, and other people such as Triton have developed a non-standard window for one of their subs, and they went through all the testing. So they basically did the Jerry Statue style testing for that one shape for their needs. They're not publishing it for everyone to use. They're keeping it close to themselves, because this way they're the only ones that take the liability of their testing and their decisions. And I applaud them for that. And they worked it out with class. Class supervised it. It all is all working out. So there are exceptions to the rule, but it's still based on the existing standards. And this is just to show what it was like back then. How they tested it, they had a weighted item following the shape of it, and then it was very sensitive and drawing on a line on a moving graph to say it was deflecting. But the picture to the right is more of interest. There was a statement made earlier that under pressure, acrylic gets soft. No, it doesn't. It doesn't get soft, but it does flow. It's a plastic. So if you put it under enough pressure, it will deform. And if you're putting it in a conical frustrum, that looks exactly like an extrusion die for metal, where you take a billet and shove it through a big hole that goes to a small hole and you get a wire. That's the same thing that's happening with the acrylic, which is why you have to design that acrylic to be massive enough with the right shape to resist that effect, and you monitor for it. But when this is from one of Jerry's papers, and he tested a failure, and he demonstrated this failure reliably happens under these conditions. And those became the conditions that he made sure were not near the line. So in fact, I had to go into this because in order to do design by analysis, we had to say, well, what good is, we had to look at the previous testing. And what I essentially was able to do was to show why the current system works. We're able to develop a methodology to reliably use FEA to achieve a safe design. It was peer-reviewed. It's been actually not just in this one ASME paper. It's been presented also at a different ASME conference, the International Mechanical Engineering Congress and Exposition, and it's been presented at Marine Technology Society. And it's gone through peer review every time. Also, it's similar to what work done by others. So there are other researchers out there doing this kind of work, and I'm using Dr. Jerry's work. They're doing the actual testing because they're working for government labs. And we're kind of coming to an informal agreement on how to do this. Our papers are going back and forth. We're even citing each other. But it's very much a stair-stepping of information and development. But the bottom line here is it is possible to do it. 20 years ago, it was assumed that you could not do a PVHO window. When I joined PVHO, the word was, well, it's just too unstable, you can't do it. I've proven it can be done. Others have gone through the review, and some of the people that were convinced it couldn't be done now agree with me because we did the work, we showed the papers, we went through informal peer review with the people that really disagreed, and they came out on the other side and said, okay, you guys, you figured it out. So that's where we are now. So it is possible to do new things, and actually some of the work that I've done and others done went into what Blanson is doing on some new shapes and what Triton has already demonstrated in their shapes. So this is the OceanGate window. What makes it different is as you look at it from left to right, it's a flat bottom, then a 45-degree angle, and then a spherical arc. Normally, you have one or the other. Normally, you have a conical frustum with a flat bottom and flat top and an angle in between, or you have a spherical sector. You'll see some analyses. You'll see analyses. You've already seen an analysis of a conical frustum in the previous slides. This is the OceanGate one. Now, this is the OceanGate window taken to 5,800 psi. This is from the short little memo. It was not a full engineering report. It was a bottom line type of report that was sent to OceanGate. And I clearly showed that the strains are well above, at this point, 8%. I say 6 here, but the top of the line is 8%. That type of profile is more localized strain. Strain is a fancy way of saying stretching. So it's not bending, it's stretching. It's locally deforming. That is inconsistent when I've analyzed all these other ones that are within code. Basically, it's like, okay, this is what code looks like. This is what code looks like. This does not look like code. And it actually looks mostly like, but not all the way like, when I replicated Jerry's test to failure, I have used transient loading, meaning I loaded it up over time so I can watch it load up. This is consistent with something on the path to failure, where a crack would initiate at that point and then dive in a little bit, and then it would actually propagate either all the way up or, that's the thing, this is an unknown shape. But when it was a conical frustum, it could either cup out the bottom or actually go all the way to the high pressure side. But that would be the crack initiation point. And the thing is that when that particular type of crack occurs, it's not a little crack that's a warning crack, like in a flat disk window. That crack runs deep. And you've at that point, you've compromised a major part of your integrity at that point. The other thing that is of note here is that the analysis I gave him showed that if you measure from the center of the inside, the dry side, it deflected 0.263 inches, a little over a quarter inch. In the news reports.
Before we go there, Mr. Newbarrow, can I just ask what this slide that we're looking at, maybe we can see the full slide, it's getting cut off, but what was this analysis? Was this done on a particular viewport, or it was the design analysis as you described using the design, just sort of what we are talking about here?
This is the OceanGate window, using the OceanGate drawing.
When you say OceanGate window, could you just specify which window we're referring to, and did you have the window itself, or was it the design of the window that we saw in an earlier slide that you used for the calculation?
This is a 2007, well, I did the work I was approaching 2017. This report was issued in 2018. This is before the window was ever made. This was
right.
The work, this is when Will Conan came to me and asked me to first review it and see what I thought of it.
Of it, sorry, just again, when you say it, what were you given?
This window.
But
you
just to
just said the
clarify,
window
it was
did
the
not-
plans of the window.
The drawings, yes, the drawings.
Okay,
Not the actual window.
understood.
Okay,
But
Yes,
Pete,
I
sorry, I
understand
just want to
now.
be clear.
I understand now. Thank you.
you never saw the actual window, is that correct?
Not in person, no. This is all before the window was made.
Okay.
So everything here that we're talking about was before this window design was ever made.
Okay, so then to clarify, you provided this report to OceanGate before
Yes.
the window was made?
That's actually the next slide.
Okay,
We'll get there. But in the news, and if you need me to, I could go and find the various reports, but there's multiple reports that came out during last summer that talked about the window would come in three-quarters of an inch, 0.75 inches. This nonlinear analysis, using the data I had at the time, using for a standardized, and again, this was a standardized acrylic material, not necessarily the ones that a specific manufacturer would use, but this is this is a representative design curve. That was only 0.26 inches. To say that something has scooched in three-quarters of an inch, I found alarming. And then it raises the question, where do they measure it from? Because it's awfully hard for a
Mr.
person.
Kemper, just sorry to interrupt you again, but when you said, when did you learn about these news reports? Was it when you were preparing these reports, or was that at some point later?
This was during during the coverage of 2023.
Okay, so can we just make that also clear for the record?
Absolutely.
and sir, I want to understand too, just to make sure I'm tracking on that three-quarters of an inch. You said you saw it in news reports. Do you know where the news media obtained that information from?
It was stated, it was during the multiple interviews of people who were saying, I'm on the Titan, I'm doing this thing with the Titan, and they would talk about it. And I think at one point it might have been, Stockton Rush was saying it comes in three-quarters of an inch. I have that information available. I have those references. It might even be in my report itself. I don't have that copy in front of me. The one I'll talk about later. But this is readily available.
Okay, so just to clarify though, I mean, we don't have factual information that it was three-quarters of an inch.
No, we don't. I'm first to say this is a report.
Sure.
But my concern is that is 3 times what I looked at when I was already for the model, and it also raises the question: how did you measure that? The way most people would measure this would not be trying to get the middle of a window. How do you do that sitting inside the Titan and watching it? You would be watching the edge of it scoot in. Well, the edge only scoots in, let's say, half that. Where the edge of the window sits in the window seat, and if you're watching that come in three-quarters of an inch, that's even further. Now, again, this was news reports. It was multiple news reports. So this was part of my reason why I contacted the NTSB, because when I read that, and it could have been someone just grossly exaggerating, but it was of significant concern, and I'll explain why that's consistent with the design as reviewed later on.
Mr. Kemper, just to clarify, so that part of this slide, that is not something that was part of your analysis in 2018. This is something you learned in 2023?
The 2 images are from my report to OceanGate. The commentary about the deflection saying in news reports, those were news reports that came about in 2023.
Got it. And sorry, can I ask one more question on this slide before we move on?
Yes.
You said that this report was prepared before the viewport was produced?
Correct.
But our understanding is that the Hydrospace viewport was delivered to OceanGate in November of 2017. That is part of Exhibit 105. So I'm just trying to understand when there's a 2018 date there, and by that time we understand the viewport had been manufactured and delivered.
That could be. I'm not part of Hydrospace. We live in different areas. What I can say is I was asked to look at this in December. I sent the memo with the results in January of 2018. I have the next slide will be a little bit more clear, and the intent was to, let's just go to the next slide. That'll just be easiest.
Understood, but I would just ask, like, if you're not certain if the viewport had been manufactured, I think that is a perfectly fine answer. But Mr. Kemper, you testified that this was prepared before the viewport even existed, and it does not appear to be the case, or
Well,
that you have knowledge of
that was my understanding until you brought that up.
Okay. So I think that, for the record, it appears that this report was done after it was the original window was manufactured and delivered to OceanGate. And we can check the delivery date on the invoice.
Right, it's Exhibit 105, I believe, but it's just if we could stick to the facts.
Sure. This is from my report. Are you okay with
I
that?
don't,
Okay.
I mean, unless we can enter, I mean, it's been in.
I'm not disagreeing, I just don't know.
Okay.
I misunderstood what the facts were.
I think we can clarify for the record here.
Not a problem.
Yeah, it looks like, just to close this matter out, it does look from the original invoice that it was November 17th, that it was.
Yeah, we can get the delivery date as well, if we do, right?
Okay, awesome.
Well, we've been going for a while. I think this is a good time for a break.
Awesome, cool.
Okay. So let's take a recess and reconvene at 4:05. During the break, we clarified the date of delivery of the first window that was manufactured for the first Titan hull. Lieutenant Steele, can you display Exhibit 105? And I'm reading December 6, 2017. So to clarify for the record, the report that we're looking at was created after delivery of the viewport and was done in 2018.
Mr. Neubauer, just to clarify, the report was prepared on the basis of the design drawing of the viewport, not the viewport itself.
That's correct. I understand it was just going off the drawings. The viewport was not delivered to to Kemper Engineering that conducted the analysis. Okay. Mr. Kemper, do you remember when you started this report and approximately when you finished it?
I started it sometime in December, and the email here on the next page is January 30th. So it's towards, it's in the formal report I sent had the original report, had dates on it, but this email went forward January 30. So of the next year of 2018.
Okay, and was this email in conjunction with delivery of the report to
Yes.
OceanGate? Okay, thank you, sir. Are you ready to proceed to this slide?
Yes, I am. Okay. So the results that were indicated here is that I indicated possible cyclic fail and then specified that the Cyclops design, that was a name at the time, it was not called the Titan at the time, at 5,800 PSI, indicates significant strain that is consistent with potential short cycle failure modes. What I was lacking, to be more definitive, was I did not have the head design. The head, I had a window seat that's basically just a mating surface, and it's very rigid, and I use it to analyze the window itself. But to actually predict the window, it's going to act as a part of the pressure vessel boundary. So to be more precise, I would want to have the actual head design, so the flexibility of that head would be incorporated in the response. So that was one of the things that that Will and I talked about, is that basically, look, Will, this looks iffy. I'm not sure. I can't say right now this is going to be one of those ones that fail in 50, 60 cycles, but I have concerns. So that was the basis of this going forward. And I was CC'd on the email, in fact, and they said, thanks, Will and Bart. I will consider this and discuss this with my team. All the best, Tony Nissen, Director of Engineering, OceanGate Incorporated. So I never heard anything more from them.
Can you explain the data you were the head design data you were seeking?
Well, just the design of the head, or what, that I didn't actually have the seat itself. If I know it looks like these metal heads are metal, and I mean they are metal, but they look like they're very stiff. They are, but when you're talking thousands and thousands of pounds of force, of pressure, it's going to deflect, it's going to move. And how that moves could make things better, could make things worse, because it's going to interact. As I said earlier, the reason why acrylic was selected, because it deforms just that little bit to the seat. And using a nonlinear analysis with contact elements, allows the seat, the window to move against the seat, and if the window under pressure, the window itself flexes, the viewport as a whole flexes as it adjusts to pressure, the window would, being nonlinear plastic model, would adjust with it. So what I had was just very much just the outside shape being held rigidly to just look to just compare that to my previous work, because that's how I was reviewing Dr. Jerry's work. Was he was using test items, I was replicating the test items that were massively rigid compared to the shapes that he was testing, and I was learning to interpret the stress strain versus the stated results. And in specific, this seemed consistent with the ones that when he tested that given design at the test pressure he used, it had an annotation of failed in 50 cycles. Another one was failed in 16 cycles. So it was not consistent with the ones that failed the first time through, but it failed under a short number of cyclic loadings, which it shouldn't do. So that's, when I saw that strain pattern, that's what caused me to be concerned and, write the letter that I did, write the report the way I did. But I could not confirm it without having that data. And also, I was using, as a material curve, there is a standard acrylic called Mill Standard P84. And that was used a lot in Jerry's testing. So because Jerry was using that in his testing, I was using that to replicate his work. Modern acrylics are cross-linked. They're stronger and better. So to actually predict the actual window results, I would also use the actual stress strain curve for that window. So when Will approached me, he did not give me details about his clients. He said, I have concerns for, can you please look at this? And I acted accordingly. So that's as far as it went at that time. My anticipation was, hey, at least ask me the question, why do you feel this, why do you feel this might be a short cycle failure? I anticipate at least a question. There was nothing that came back. Not well, will it leak or will it crack? Or no questions about what the failure mode would be. What should we anticipate? If we use it, what would it look like? So there was no interest in any communication whatsoever. They didn't even ask me, how'd you come up with this, to see if I was modeling this the right way. They didn't have any interest in talking to me about that. So, that's as far as that went at that time. I found that a little bit disturbing, but I'm not the only engineer out there. And there are other people doing things. And can I go back and talk about what I spoke with Stockton Rush in 2016? It applies to this.
Can you clarify, was that at the annual meetings?
At Underwater Intervention Marine Technology Society meeting in New Orleans in 2016.
Yes, sir.
Okay. He made it very clear that I may have an aerospace degree, but I'm not the engineer. I'm going to hire an engineer who knows what they're doing. That is the right answer. And that to me, I just met the man. I didn't know him. That to me seemed absolutely reasonable. That great, you have a technical background, but being the engineer is a full-time job, and that's your whole focus. And you don't want the money guy to also be the person being the engineer. Because if I was the money guy at my company, I would have all the toys, and we wouldn't be paying bills. So him saying that I would, I'm going to hire these really good engineers and consult with people, it's like, okay. So my thought was that I informed him, he wasn't sure about it, and he went to his team, and that's what they said. I'm going to go talk to my team about it. So I was not concerned as in, oh my God, I think these people are going off the deep end. I figured they just took their work to their team and went to their people and figured and made a decision based on that. So I had a basis by which to interpret this, that when they said my team, that knowing that he's working on submarines, that he is talking to some of the other people in this field that are doing good work.
Sir, so you did not follow up beyond this email?
No. If I would have felt the need to, I would have. If I would have actually felt more concerned, I might have gone to the Board of Registration or some other, I would have acted in a more decisive manner. But I had every basis to think the Stockton Rush would be acting in a reasonable manner.
Understand. And sir, I'd like to just ask a question about the 0.26 inch expected distance of on the previous slide. You had estimated, I think, 0.26 inches of movement.
Correct.
Of the bottom of the window along the seating surface. Is that correct?
No, I estimated 2.6 inches along the center line. So it would be basically, as you look at the window, at the round window, it'd be the middle. Because it would pooch out, it would pooch out in a dome. So it would be, be a round dome and be right there in the middle. So that was why I'm saying that's more difficult to track, but the edge of it where it's riding the window seat is much easier to measure. And that's why I thought that a layperson, when they said they saw it move 3/4 of an inch up and down the window seat, I was concerned that might be what they're measuring, because that would be more extreme than just what I had.
And just to clarify, it is 0.263 inches.
Yes, 0.263.
Would there be a concern if it was greater than that by a margin of double?
By a significant margin, times 3 is significant.
But what would be a possible cause? What does that indicate, in your opinion?
I have slides that address that.
Okay. Let's proceed.
Okay. So is everyone good with this slide right now? We can move to the next one. So what we have next is the conical section, spherical sector window that would sit in the same space as the OceanGate one. So in other words, the top rounded part is still there, and then you're just putting in less acrylic. We're just making this a spherical sector. And the right image was from the SolidWorks models that I developed, where I had the SolidWorks model of the Cyclops window, later became the Titan on top, and bottom was the alternate design using a spherical sector. Now this was developed, this analysis coming up was done post-incident. So this is when I knew that I was going to submit something to the NTSB. I anticipated the questions would be, well, what would happen if you use a spherical window? What about this? What about that? Also, as of 2003, I had 5 more years of working in design by analysis. I had a little bit more refined my techniques. More people had published. I had published more. So I had a little bit more of a refined technique when it came to modeling. I chose not to redo my old work and just present what was done in 2018 as transmitted. So the next one.
Mr. Kemper, just to clarify, the image on the left is not the design of a viewport that was manufactured for OceanGate. The one on the right is that
the one on the left was not for OceanGate. The top one on the right was for OceanGate. The bottom one on the right is the same as the one on the left.
Okay, thank you.
Not a problem. Okay, this is how simple Jerry Statue's method is. So the critical dimension to do this is going to be the bottom of the window seat, which right there is 15.2 inches. So I need that number. I need to know, and since this is a non-standard window, I selected that this was going to be similar to an acrylic spherical window with a conical edge, because I needed something to use Jerry's method. And due to the depth it was diving to, it has what's called a CF of 4. You look it up for the temperature. It's going to be 50 degrees, CF 4. It's that simple. Now, the CF is correction factor. That is not a design margin. It's not a safety factor. In fact, Kaylee Williams of Lockheed Martin and I presented a paper several years ago where we went through the CFs and tried to figure out, is that an actual design margin, or is there a relationship of CF to design that we could pull as a design margin, so we could basically back out how reliable, what the safety margin is for Jerry's designs. And we could not find a correlation. It works, and some are more conservative than others, but it's not a design margin, and you cannot treat that as a design margin. But you take that, you multiply your design pressure times 4, I get a number, 23,200 psi or 160 megapascals. Then I find the right graph in the book, and because it's 90-degree angle or 40, a 90-degree included angle on the window seat, I'm using 160 because the other one, that's the other side didn't have the US one. You go to 90 degrees, you drop down, and it gives me a T over DI, which is the thickness over the diameter. That now gives me my thickness. It's that simple. At no point am I putting a single material property in here. I could double and triple the material strength. I could increase the stiffness. The design does not change. This is why we're doing design by analysis, and it's a slog to do this. And if you would have presented this to me as a good idea on its own, I would have a lot of issues. But this has 70 years of proof, and before they even did that, they had 20 years of testing to back that up. So I know this is shockingly simple for such a critical item, but when people say that Jerry Statue was conservative in where he put his design lines, he was, because of the uncertainty, because at that time, with the tools available, there was just not a reliable way to model this directly with mathematics like we would a beam calculation. So that is the PVH01 design method. Now, there is more art and science where you're doing the window seat, the whole mechanism and how it interacts with your rest of your pressure vessel. There's a lot more to it, but the acrylic section, that's it. I know all the technical people are going, this can't be that simple, but it is. So let's go to something that's not as simple. Let's go to the next slide. This is showing the Titan window, the Cyclops 2 window, and then the exact same seat and same spherical section and as a spherical sector. They both deflect about the same amount. Axial deflection on the bottom left is 204 inches. Again, I'm using a more refined method than I did 5 years prior. With the spherical sector is 0.18. However, look at the strain. On the left-hand side, peak strain is around 16%. It's highly, highly localized. And when you see very localized strain, that is consistent in any material with a potential tear or cracking. I mean, all the energy, all the pain and suffering is going that one small point. And typically, acrylic has a max strain somewhere between 4 and 8%. So this is also showing that you're likely to have exceeded it, and you probably had some gross local deformation, but all that residual strain is in there. Now you look at the spherical sector, peak strain is 0.25%, much lower. Still pretty much elastic. And the elastic part is not just about the peak strain, it's also about how the rest of the material stays well in the elastic region and forces the whole thing to act as a unit in an elastic manner. So this raised significant questions, which is why I did the next analysis.
Mr. Kemper, before we go to the next one, I just
Sure.
wanted, and for the record, none of this seems simple to me, so the prior slide or this one, but the post-incident analysis, what was that done? I assume the incident is the Titan tragedy. What was the analysis done? What were you using for the analysis?
I still had the same model, the same geometry from previous. So I used the same window design that was presented to me in 2018. And then I used I confirmed Will Conan's spherical sector design. He said that he did it according to PVHO. I backed out and got the same numbers he did. And that was what I did to compare the two. Because there's a legitimate question, what would happen one window versus the other in terms of looking at this from a failure analysis or a systems perspective, which is my intention with going to the NTSB. This was not meant to be, and I didn't go to Will with this. This was not about Will's choices, or not about OceanGate. This was submitting this to a jurisdictional authority for them to decide whether it's relevant or not. I honestly didn't know if my report would be seen as relevant, but I knew I had to submit it.
Understood. So just to clarify, it's basically additional analysis on the data that you had from 2018. Is that
Correct.
fair? Understood. Thank you.
Not a problem.
Sir, did you have any updated information on the seating surface at this time?
No, I did not. I did not have the designs of the head.
And can I clarify also that on the left-hand graphs, that would be the Titan's design, and then on the right-hand side, that would be just a window that is curved?
That is an ASME PVHR1 spherical sector. So the point of it is, it's not a question of that Will was looking at this. I did the work to verify this is for that critical dimension and that pressure, that is going to be the ASME design that you get every time. Okay. Now, we've talked about elastic and plastic, and we talked about how plastic by nature stays bent. You bend it and it stays bent. That's the definition of plastic when you're talking about metals. So, as I said, I had some more experience at this point, and there's been more studies put out at this point. So if you can go to the next slide, what I'm going to show here is a loading and unloading, where the curve on the left shows that it's called a pseudo time load. In other words, it's actually not representing any particular time period. It's just saying I increased the load up to the max amount at a certain rate. As you got closer to a certain rate, it curves over and slows down the rate. In the middle of the curve, which would be 0.5 seconds, it's not actually seconds. It's just 1 second is unity, so 0.5 is half that time period, is at peak, and then it comes back down. The reason for this is that when you're looking at nonlinear curves and things stay bent, it's all interacting because you have the parts that are still very plastic but compressed like a spring, and they're pushing back. And then you have the parts that have been deformed, and then they can be deformed back into a shape. So by loading and unloading, I was able to use this technique to replicate some of the impending failures from Jerry Statue's work. So this one cycle load is not meant to be used for fatigue loading or for something like that, but it is, I did find this to be a much more precise way of looking at a window with respect to failure modes as verified by comparing it to Jerry Statue's data. And when I say Jerry Statue's data, when he presented his papers, he included his test methods, his uncertainty. He would have large appendices to his actual paper that was published. In the Navy papers, he would have all the extra data available. So I was basically able to go through his lab reports and get his notes on that. So this is showing that it's a refined mesh without going into detail. You want finer mesh where you're having a lot more things going on with the stress and strain. It goes to how large the model is in the computer, but what this is meant to say is that there's a pretty good, this is something that my professors would arguably call overmeshed. But with modern computers, I can overmesh something and let it run and get it faster than back in the old days when we had to literally plot every little mesh point by hand and type in the commands. So it wasn't uphill both ways, but it felt like that. So can we go to the next slide, please? So this is the result of one cycle. Going into 0 point on the way up means nothing because it's not loaded. So I'm comparing 1,000 pounds of pressure, 1,000 psi on the way up, and then 1,000 psi on the way down. The top picture is on the way up. The bottom picture is on the way down. The difference of what you're seeing is residual strain. In other words, and also if you look at the top picture, you'll see a little bit of white space. Even at 1,000 pounds, it's still loaded. It's already pulled away from the window seat. That white space is to scale. What this means is that it was pushed down, and that flat part at the bottom was permanently deformed inwards, very much like an extrusion die. Now, the top part is elastic because it has it's not as directly, you can see it doesn't show all the strain. So the top part is very elastic. It's not permanently deformed. So as you take the pressure off, it pulls it back up because you have it pressed down. It's acting like a spring. You take the pressure off, it's pushing itself back up, just like it would in real life. What's significant about that is that every time you cycled this will happen again. In other words, every time with this particular design, every time you cycle with that high localized strain, it's going to push it again and push it again and push it again. Now, what's going to happen over time, a number of cycles, is the top of the window is going to be in full contact with the window seat because it's elastic. It's going to be right back where it started. It'll be right back where it started, but the inside, on the low pressure side, is going to have a gap. And it's going to be watertight because the top side is the water side. But now when you press on it, there's going to be a period, a space where there's only a little bit of contact at the top, and it's going to scoot down quickly until it picks up the rest of the material, until it picks up the corner, and basically. Because if you now have taken it and pulled the angles in a little bit, only the parts that are in contact are providing resistance, and it comes in more. So when I did this analysis, again, I was trying to get a better handle on this design, and the open source news, which is not engineering data, said it came in 3/4 of an inch. This behavior is consistent with the model, that over time, it would have deflected in such a way that as it pressurizes, it would scoot in rather quickly until it picks up the last point that it was fully engaged, and then fully engage and take up the load again. This is an example of why the ASME designs, whatever Jerry did, how much testing he did, paid off because those conservative curves kept us away from this behavior. But this behavior here is consistent with potential failure.
Sir, I want to follow up on that. So does that mean, in your opinion, that this design is problematic with a flat surface?
Absolutely, yes. Now, I want to caveat this. This has, and now that we could do this will be for the later report. Now that we have the step file of the head, and we know what the material is because we know it's now grade 3 titanium, we are now in a position to give a more precise answer. This is from the report I did for the NTSB last year around the September-October timeframe. So we did not have the ability to give a more precise answer. But this, given that it was just an in-house review, let's see what it looks like using the one cycle load, since it was consistent with the potential failure mode, these results are what prompted me to say, I need to send this to NTSB and let the smart guys there take care of this.
Sir, did you run this for like a second cycle, this analysis?
I didn't. And there's several reasons for that. But basically, it was all my previous work was just looking at one cycle. I haven't, if you start looking at multiple cycles, then you have to start asking the question of creep. Now, creep is the issue of a material, any material, steel does this too, under the right conditions, where under a static load, it just kind of moves. It's not quick, but it moves. Acrylic will creep. So if I was going to look at more at multiple cycles, I would have to consider time factors, and that would go in. I'd have to know more about what's going on. And honestly, it's a fairly involved calculation. The setup, and then I had no means to validate it. So I might get a very precise answer and be still way off because I have the wrong material properties, or I have, all of this was done using my default military grade acrylic that was done for Jerry's work, because I was trying to validate the process, the technique against Jerry's work. I didn't have the ability to find out who made the window I didn't know the details of the window enough at this time. This was an in-house exercise to see if there was a reason to act, and these results led to me sending a report to the NTSB.
Yes, sir, I understand. Thank you.
So this concludes the windows portion of the report. So the next slide is going to the titanium heads and domes. A question that came up during last week's presentations was, what's the difference between grade 5 and grade 3? Grade 5 often is listed as titanium, 6 aluminum, 4 vanadium. That's grade 5. Grade 3 is grade 3. You've reduced your yield strength to 45% of grade 5, and you've basically cut your tensile strength in half. So that's the difference between grade 5 and grade 3. But when we did the analysis using the step file from OceanGate, so we actually had the actual geometry, our initial analysis, now this is a linear analysis, but it indicated there was no real problem here. So once we saw that it behaved in an appropriate manner, that the stress distribution concentrations were consistent with normal practice, and even though there's a small quote-unquote hotspot where there's a little bit of high stress, that's not unusual with thick elements, and those will self-relieve. No failure mode was indicated, so we moved on.
And sir, I just want to clarify also that all of the results you're discussing now were done post-incident.
Yes. The results here were done in conjunction with the material provided by the U.S. Coast Guard, in conjunction with our helping out the MBI.
Thank you, sir.
So that concludes the first half of the testimony of Bart Kemper. If you've made it this far, I hope you found it an interesting watch. Even looking past all of the data discussed and the analysis performed, I also found it helpful in gaining some clearer focus on that time when Hydrospace manufactured that early window. The timeline of when both the window and the analysis report were completed and delivered, and what OceanGate's response was to being presented with concerns. Which itself was not surprising, given what we've already heard previously, but still, it's always nice to see it there in black and white. As stated numerous times in the past, the goal of this OceanGate playlist of mine is to present the facts in a relatively linear fashion to provide a timeline for anyone who watches. I do of course give my thoughts in the videos, just like I'm doing now, but usually only to speak about those facts, as I'm obviously no expert in this field, and so sometimes, especially when things get overly technical, it can be hard to fully absorb how weighty or truly significant something like the presentation in this video can really be. What I mean is, I don't really feel completely comfortable leaning too heavily into the report in terms of its own weight, as obviously the graphs showing the strain data on the window and the window seat for example, and the concerns they raised are worrying, both those created before and after the incident. It's just when it's made clear by either the Coast Guard or OceanGate's representatives that they are based from drawings and off presets that didn't match the actual design, like its materials, if I understood that correctly. It makes me kind of hesitant to go full in, like, look at this damning report of OceanGate. And it's not that I'm questioning Mr. Kemper's data in any way at all, I'm stressing the fact that I'm in no position to do it. Also, it's stated that the post-incident analysis was only ran once by Mr. Kemper. Is that enough? Even though it predicted a problem right away? Who am I to say? It's just more to do with me, being someone who is learning as much as I can as I go. I just don't feel I have the best grounds for truly evaluating the report's ins and outs. But I would of course love to hear what you all have to think and say about it too. I ended this video at a fairly natural transition in the testimony from the window, O-rings and end caps to now moving on to carbon fibre in part 2, as well as a failure and root cause analysis, so it will be nice to cover that and no doubt hear some conclusions from the data we've already seen. I will be sure to have that video up in a couple of days after this one, by the way. So here is a list of the testimonies that still remain. These took up the last 2 days of the hearing, and so I doubt that any of them will be as long as this one is. As you can see, we will be hearing from representatives of NASA, Boeing, and then a flurry of Coast Guard representatives, as well as Matthew McCoy, a former OceanGate employee, someone whose testimony was included in the recent Netflix documentary. These remaining testimonies will be completed by the end of August at the latest, and my upcoming OceanGate documentary that I'm currently working on, and I'm incredibly happy with so far by the way, will hopefully be out in September. And as the Coast Guard's final report was slated to be released later this year, this may fit well with my coverage, with only a slight gap in between. Anyway, just a little heads up on all of that, and I can't wait to share my documentary with you all. So I will wrap this video up here, and no doubt have more to speak about regarding this testimony at the end of part 2, which, once again, will be uploaded very soon. But until then, thank you all so much for watching this video, it is greatly appreciated, and bye for now.